Our lesson in integrals and integration is theorems on antidifferentiation. At the end of this lesson, the students are expected to be able to first, apply theorems on antidifferentiation. Second, compute the general antiderivative of algebraic functions. And third, recognize the use of integral notation as a way to easily represent the relationship between a function and its general antiderivative. Recall that the derivative of a function f is denoted by f prime of x, y prime, d over dx of f of x, dy over dx, or d sub x of f of x. A convenient notation that we can use in finding antiderivatives is the symbol for indefinite integral. It looks like an elongated S. Gottfried Wilhelm Leibniz was the first to use the notation to represent the operation of integration. The antiderivative of a function f is synonymous to the indefinite integral of a function f. Hence, if the capital F of x at c plus c is the general antiderivative of a function f, then we write the integral of f of x dx is equal to the capital F of x plus c. With your knowledge that antidifferentiation is the inverse process of differentiation, you now know how to find the antiderivative by working backwards using the derivative formulas. However, the task can be painstaking when it comes to complicated functions. Useful theorems can be utilized to easily find the general antiderivatives of functions. Considering that antidifferentiation is the inverse process of differentiation, the following theorems can be easily proved from their corresponding differentiation theorems. Theorem 1. The integral of d of x is equal to x plus c. This is like saying that the integral of 1 dx is equal to x plus c. Theorem 2. The integral of a of f of x dx is equal to a times the integral of f of x dx plus c, where a is a constant. Theorem 3. The integral of a sum of two functions is equal to the sum of the individual integrals plus c. That is, the integral of f of x plus g of x dx is equal to the integral of f of x dx plus integral of g of x dx plus c. Theorem 4. If f sub 1 to f sub n are defined on the same interval, then the integral of the quantity c sub 1 f sub 1 of x plus up to c sub n times f of n sub of x dx is equal to c sub 1 times the integral of f sub 1 of x dx plus up to c sub n times the integral of f sub n of x dx, where c sub 1 to c sub n are constants. Theorem 5. If n is a rational number, then the integral of u raised to n du is equal to u raised to n plus 1 all over n plus 1 plus c if n is not equal to negative 1, and the natural logarithm of the absolute value of u plus c if n is equal to negative 1. We can prove Theorem 5 by using the derivative of the function. If we take the derivative of u raised to n plus 1 all over n plus 1, so we are just using the power power rule. So we have n plus 1 times u raised to n all over n plus 1 is equal to u raised to n, where n is not equal to 1. If we take the derivative of ln of the absolute value of u, then we have 1 over u, or that is u raised to negative 1. Theorem 4 is a combination of theorems 2 and 3. Theorems 3 and 4 holds true for subtraction as well. However, it should be noted that the integral of a product or quotient of two functions is not always equal to the product or quotient of the integrals of the two functions. Let's take a look at the following examples. Find the general antiderivative of f of x equals 9x squared plus 2x minus 5. By Theorem 3, we have integral of 9x squared dx plus integral of 2x dx minus integral of 5 dx. By Theorem 2, we have 9 times the integral of x squared dx plus 2 times the integral of x dx minus 5 times the integral of dx. Then by Theorem 5, we have 9 times the quantity x cubed over 3 plus c sub 1 plus 2 times the quantity x squared over 2 plus c sub 2 minus 5 times the quantity x plus c sub 3. Simplifying, we have 3x cubed plus x squared minus 5x plus 9c sub 1 plus 2c sub 2 minus 5c sub 3. Note that 9c sub 1 plus 2c sub 2 minus 5c sub 3 is an arbitrary constant which is just equal to c. So we have 3x cubed plus x squared minus 5x plus c. In the succeeding examples, we will refrain from including plus c in the integral of each term. Instead, we will just indicate plus c at the end of the integral. Example 2. Find the general antiderivative of f of x equals 12x cubed plus 3x squared minus 4x minus 10. By Theorem 3, we can get the individual derivatives of each term. So we have integral of 12x cubed dx plus integral of 3x squared dx minus integral of 4x dx minus integral of 10 dx. By Theorem 2, we can factor out the constants. So we have 12 times the integral of x cubed dx plus 3 times the integral of x squared dx minus 4 times the integral of x dx minus 10 times the integral of dx. By Theorem 5, we have 12 times the quantity x raised to 4 over 4 plus 3 times the quantity x cubed over 3 minus 4 times the quantity x squared over 2 minus 10 times x plus c. Therefore, the antiderivative of the function is 3x raised to 4 plus x cubed minus 2x squared minus 10x plus c. Example 3. Find the general antiderivative of f of x equals x raised to 5 minus 5x cubed plus 8x. By Theorem 3, we can get the individual integrals of each term. So we have integral of x raised to 5 dx minus integral of 5x cubed dx plus integral of 8 of x dx. Then by Theorem 2, we can factor out the constants. So we have integral of x raised to 5 dx minus 5 times the integral of x cubed dx plus 8 times the integral of x dx. By Theorem 5, we have the quantity x raised to 6 over 6 minus 5 times the quantity x raised to 4 over 4 plus 8 times the quantity x squared over 2 plus c. Therefore, the general antiderivative of the function is 1 over 6 times x raised to 6 minus 5 over 4 times x raised to 4 plus 4x squared plus c. Example number 4. Let's evaluate the integral of 27t raised to 3 minus 1 all over cube root of t dt. So we can rewrite the function by distributing the numerator to each term of the distributing the denominator to each term of the numerator. So we have the integral of 27t cubed times t raised to negative 1/3 minus t raised to negative 1/3 dt. Then by theorem 4, we have 27 times the derivative of t raised to 8 over 3 dt minus the integral of t raised to negative 1/3 dt. By theorem 5, we have 27 times the quantity t raised to 11 over 3 all over 11 over 3 minus the quantity t raised to 2/3 all over 2/3 plus c. Therefore, the value of the integral is 81 over 11 t raised to 11 over 3 minus 3 over 2 times t raised to 2/3 plus c. And finally, let's evaluate the integral of the quantity 2 over x cubed plus 3 over x squared plus 5 dt. Again, we can rewrite the function as 2x raised to negative 3 plus 3x raised to negative 2 plus 5 and get the integrals of each of the terms. So we have by theorem 4, 2 times the integral of x raised to negative 3 dx plus 3 times the integral of x raised to negative 2 dx plus 5 times the integral of dx. By theorem 5, we have 2 times x raised to negative 2 over negative 2 plus 3 times the quantity x raised to negative 1 over negative 1 plus 5x plus c. Therefore, the value of the integral is negative 1 over x squared minus 3 over x plus 5x plus c. Now, it's time for you to apply what you have learned. So, pause this video to answer the following indefinite integrals. Check your answers if you got the right answer. Thank you.